Hello everyone, today I am going to discuss the most important and interesting topic, Jahn-Taylor theorem or Jahn-Taylor distortion. This topic is important for CSIR NET, GATE, IIT JAM and MSc entrance, so please don't skip the video. Now, Jahn-Taylor theorem states that any non-linear molecule is an electronically degenerate state, is unstable, and the molecule becomes distorted in such a way as to remove degeneracy, lower its symmetry, and lower energy. One by one, I will discuss. First, any non-linear molecule. So, suppose example CuH2O whole 6 2 plus. This is non-linear molecule. Suppose iron L6 2 plus. This is also non-linear molecule. Platinum Cl4 2 minus. This is non-linear molecule. So, non-linear molecule. In case of non-linear molecule, Jahn-Taylor theorem valid. But suppose example Ag ammonia whole 2 plus. This coordination number 2. This is linear molecule. So linear complex. So Jahn-Taylor theorem. In case of linear complex, this is invalid. So non-linear molecule Jahn-Taylor distortion valid, linear molecule Jahn-Taylor distortion invalid. Now second, electronically degenerate. What is electronically degenerate? Suppose example D1 in octahedral complex. First, free metal ion 5 d orbital are degenerate. Second, in presence of ligand, the 5d or d orbital are split out. One is T2G and another is Eg. Now, in case of D1, one electron is there, so T2G 1 electron. So this electron either this position or middle position or sometimes last position. So the degeneracy 3, T2G degeneracy 3. So this is the electronically degenerate state. Some examples are D3. In case of D3, this 5d orbital, D3 1 2 3 electron spread out, T2G and Eg, T2G 3 electron 1 2 3. There are no degenerate state. So this is non-ED state, electronically degenerate state. But invalid Jahn-Taylor theorem is electronically degenerate state, non-electronically degenerate state. So non-ED state, there is Jahn-Taylor theorem is invalid. Only ED state, electronically degenerate state, the Jahn-Taylor theorem is valid. This is valid Jahn-Taylor theorem. Now in ED state, the electronically degenerate state is unstable state. This is unstable state. So form the lower symmetry, remove the degeneracy and lower the symmetry to form the lower energy. This is stable state. Now, in case of octahedral, 5d orbital are degenerate in free metal ion, free metal ion. 5d orbital are degenerate. Then further split out. One is T2G and another is Eg. We know T2G having orbital dxy, dyz and dxz, and Eg having orbital dx square minus y square and dz square. In presence of non-linear molecule and ED, this electronically degenerate state, so T2G further split out. So this is the Jahn-Taylor distortion split out. One is dxz, dyz and dxy, and Eg split out. This dxz, yz same symmetry, dz square and dx square minus y square. This is the case of jet out system. So In octahedral case, the metal in presence of ligand, this T2G and EG split out. Then in this situation, the ligand in axial position are elongated. Jet out sometimes calls it is axially elongated, or it is called tetragonally elongated. So first, in free metal ion, 5 d orbital are degenerate. In presence of ligand, 5 d orbital are split out. One is T2G and another is EG. And then T2G in electronically nonlinear molecular and electronically degenerate state. Suppose in 1 electron is there or 2 electron is there. This case of D2 electronic state. So 2 electron is there, and this is electronically degenerate state because T2G is 2 electron there. So this is the electronically degenerate state. So this is electronically degenerate state. This is unstable. To form the stable, the remove is degeneracy. So 2 electron is there. So this is a symmetrical manner. So unsymmetrical to symmetrical. This is the Z out case. Next, I will discuss Z in case. Now 5 d orbital similarly split out T2G and EG, and further split out the two. First one is dxy and another two are reverse order, another two are dxz and dyz. Similarly, dxz higher energy, so this symmetry dz square higher energy, and then dxy less energy, so dx square minus y square less energy. This is the case of Z in case, or sometimes this free metal ion and metal in presence of ligand in octahedral field. In our octahedral field, metal in presence of ligand. After Jahn distortion, the metal and ligand, some ligand are small and full ligand are long. So 2 ligand are short and 4 ligand are long. So this is axially, sometimes this is axially small, so axially compressed, or this is tetragonally compression. So first metal in presence of ligand, so T2G and EG, and then split out dxy and dxzyz, and EG split out dx square minus y square dz square. This is the Z in case, and metal, this is the axial compressed, and this is also called the tetragonally compression. Now Jahn distortion in octahedral complex. Jahn distortion in present in case of suppose D1 there is T2G 1 EG0 T2G1. This is electronically degenerate state. First I discuss electronically degenerate state. And suppose D2 is T2G2 EG0. This is also the electronically degenerate state. There is 3 degeneracy. Suppose D4 high spin case. So T2G 3 EG1. So there is also 1 2 3 EG1. So there is also degeneracy 2. This is also electronically degenerate state. So T2G and or EG are unsymmetrically filled electron is called electronically degenerate state. So T2G or EG unsymmetrically filled electron, this is the ED state. Suppose EG1, this is unsymmetrically filled, T2G2 unsymmetrically filled. So this is the ED state, and ED state Jahn distortion valid. And absence in D3, D6 low spin or D8. This is the absence. JTD Jahn distortion equal to 0. But CFSC in case of D3, D6 low spin and D8, CFSC is maximum. In case of D3, D6 low spin and D8 CFSC maximum. And also D0, D5 high spin, also D10 is Jahn Taylor distortion also 0 absence, and CFSC also 0. So conclusion that CFSC equal to 0, so must be Jahn Taylor distortion equal to 0. But Jahn Taylor distortion equal to 0, we cannot say CFSC equal to 0. CFSC either 0 or CFSC not equal to 0. So D3, D6, D8, the Jahn Taylor distortion equal to 0, but CFSC maximum. So we cannot say the Jahn Taylor distortion equal to 0, CFSC equal to 0. But CFSC equal to 0, Jahn Taylor distortion must be 0. Now, in case of T2G is unsymmetrically filled electron. Unsymmetrically filled electron. Suppose in case of D1 octahedral case. D1 octahedral case, 5 d orbital are split out and 2 are T2G and EG. The 1 electron is there, so 1 electron. And further split out either Z out or Z in. 2 are sketched. So this is dxz, dyz, and this is dxy, and this is dz square, and this is dx square minus y square. This is z out case. Second, z in case, T2G and T2G is further split. This is dxy and this is dxz, dyz, and EG split dx square minus y square and dz square. This is EG, this is T2G, and one electron is there. Now this one electron, if this position and this one electron in this position, this is the electronically degenerate state. We know this is T2G unsymmetrical field, so this is unstable state, and this is also the electronically degenerate because one electron is there and same times one electron is there, so these are degenerate state 2. This is also electronically degenerate state. This is also unstable, but in case of this there is electronically non-degenerate state. So this is the stable state, this is stable state, so the form is Z in. So D1 octahedral is Z in also Z in type. Similarly, in case of D2 octahedral, suppose there is 2 electron and there is 2 electron. So T2G 2 electron and T2G 2 electron, and there is also 1 electron. But in case of this is electronically degenerate state unstable, but this is stable because this is electronically non-degenerate, but this is also the electronically degenerate. So in case of D2 this is the most stable form, Z out is the most stable form. In case of D2 is Z out form is the most stable form. Remember this thing is, we know that T2G and EG the energy gap is delta O. This is the CFSC value, and this is also the Jahn Taylor distortion energy. This is delta 1 and this is the splitting energy delta 2. So delta O greater than equal to delta 1 greater than delta 2. Why delta 1 greater than delta 2? Because EG is ligand approach in EG state is along the axis. So along the axis is more splitted, but in T2G in between the axis. So ligand approach in T2G, so in between the axis, so the splitting energy is less. The interaction is less, so the splitting energy is less. So delta O, this is the CFSC value, CFSC total, this is the CFSC, and this is the Jahn Taylor stabilization energy. Jahn Taylor stabilization energy. Delta 1 and delta 2 are Jahn Taylor stabilization energy. The energy, this is half is plus delta 1 by 2 and another this is minus delta 1 by 2, and similarly this upper part is plus 2 delta 2 by 3 and lower part is minus delta 2 by 3, and similarly this is delta, this is the del O, this is CFSC value, and this is Jahn Taylor distortion. Higher part is plus delta 1 by 2 and lower part minus delta 1 by 2, and similarly upper part is, this part is minus plus delta 2 by 3 and lower part is minus 2 delta 2 by 3, and calculate this is the total JTAC. And in case of EG is unsymmetrically filled electron. Now similar, suppose example D4 high spin case. Similar, this is 4 electron 1 2 3 4 and split out. This is octahedral case. Split out, this is T2G and this is EG. 4 electron 1 2 3 high spin case, so this is, and T2G further split out in either this is dxz dyz or dxy, and this is dz square or dx square minus y square, or similarly, and another, this is z out and similarly z in, this split out, this is dxy and this is dxz yz, and similarly this is dx square minus y square and this is dz square. 4 electron 1 2 3, and remember that delta 1 or delta 2 pairing less than equal to pairing energy. No force pairing is possible. No force pairing is possible. So this is D3, T2G3 1 2 3 and EG1, this is 1 electron, or sometimes this is 1 electron. So we cannot say the EG unsymmetrically filled EG1, this is T2G3 EG1, and EG1 state, this is either Z out, similar symmetrical, this is also symmetrical, this is stable, and this is also symmetrical, this is stable, electronically non-degenerate state, so this is also stable, this is also stable. But so EG is Z out plus Z in, both possible, Z out and Z in both possible, but we cannot say in Jahn-Teller distortion predominant, which is predominant. So with the help of X-ray or some spectroscopy, we say the EG1 or EG3 from the Z out is prefer or dominant, because the Z in dz square orbital there is two lobe interaction with the ligand, but in case of dx square y square, dx square minus y square, there is 4 lobe interaction with ligand. So there is more interaction, more repulsion, there is unstable state, unstable. So dx square y square unstable, higher energy state, and dz square 2 ligand are interaction, so this is stable state. So Z out, dz square lower energy and dx square higher energy state, this is the Z out state, is stable. So EG1 and EG3 only for Z out, but both Z in and Z out in case of Jahn-Teller distortion both are possible, but Z out predominant reason, Z in or Z out. This is the summary. EG1 or EG3 or T2G2 or T2G5, T2G1 or T2G4. In EG1 and EG3, Z in plus Z out both possible, but Z out dominant, but T2G2 and T2G5 only Z out possible, but in case of T2G1 and T2G4, Z in possible. Remember the tricks, Z in or Z out, this is EG1, EG3 and T2G2, T2G5 and T2G1 and T2G4. Third, Jahn-Teller distortion order. First, we see EG unsymmetrical greater than T2G unsymmetrical. Jahn-Teller distortion order. EG unsymmetrical or greater than T2G unsymmetrical. EG unsymmetrical, EG3 greater than EG1, and then T2G unsymmetrical. but 4D, 5D greater than 4D greater than 3D. The Jahn-Teller distortion order is AU2 plus greater than AG2 plus greater than CU2 plus. This is 5D, 4D and 3D greater than chromium 2 plus high spin greater than T2G unsymmetrical case. Now, because the EG3 the interaction Jahn-Teller distortion is high than the EG1 and then the T2G unsymmetrical field. This is the order. Second, Jahn-Teller distortion proportional to oxidation state of transition metal, oxidation state of transition metal. Now, Jahn-Teller distortion increase the stability of complex increase. Suppose example, in case of copper L6 2 plus greater than of nickel L6 2 plus, where a ligand non-chelating. In case of copper L6 2 plus greater than nickel L6 2 plus, a ligand in non-chelating. In octahedral case, in case of octahedral, the order of the Jahn-Teller distortion is Mn2 plus greater less than of Fe2 plus less than of cobalt 2 plus less than of nickel 2 plus less than of copper 2 plus, but copper is more Jahn-Teller, so this is Zn2 plus. This is the order of Jahn-Teller distortion in octahedral complex. Copper 2 plus is higher Jahn-Teller distortion, so stability increase. So copper 2 plus ligand in octahedral case, so the stability order copper 2 plus greater than nickel 2 plus, because Jahn-Teller distortion is high in copper 2 plus. So next day I will discuss square planar complex and static and dynamic Jahn-Teller distortion, application of JTD, and please stay with me, like, share, subscribe, comment. Thank you.